All right, welcome to part 3 of 4.6. This one we're going to keep gradually going to more calculator to get our answers. So here we have a polynomial function for f of x equals x to the fourth minus 12x to the third plus 48x squared minus 64x. It's a polynomial function, so there will be no vertical asymptotes, no horizontal asymptotes. Polynomial functions never have those. And we want to graph this in the following window. So I kind of played with the window to give you good numbers to work with. So I'm going to put in a plus 0 to complete my polynomial because it should end at a constant. The reason I want that there is because that's going to be my y-intercept. It's always whatever the constant is. To find my x-intercepts, we're going to have to set this equal to 0 and solve. So I factored out an x, set it equal to 0. And, years of experience gives me a little knowledge here for tricks. I noticed that this x is going to give me an x-intercept of 0, 0. I got to solve this trinomial, and you could probably try factor by grouping, but you're going to notice it's not going to work. But if you look really close at the pattern of the numbers here, this is 1 times x cubed minus 3 times 4, and I'm going to put it to the first so it helps you see the pattern, x squared, plus 3 times 4 squared times x to the first minus 1 times 4 cubed. Let that sink in there for a little bit, and that is the binomial expansion theorem. Here's that row 3, 1, 3, 3, 1. Notice that the powers on the x's are descending until it's x to the 0 down here. And the 4s, they are ascending. This is technically times 4 to the 0, then times 4 to the first, 4 to the second, 4 to the third. So that whole thing factors to x minus 4th to the third power, which tells me x equals 4. It's just that there's going to be 3 of them, so I've got to keep that in mind when I want to graph it. That means it's going to look like a little bit of a cubic curve right at that x-intercept. So speaking of graphing, let's go type it into y1. Let's go look at its graph. And sure enough, there's one x-intercept right there at 0. I come down, and we're definitely coming back up. And here's my other x-intercept at, come on, mouse. Sorry about that, at 4, 0. And that's where I get that cubic looking curve right there because this occurred 3 times. So I can see we definitely have a local min right here, which means we're going to have a horizontal tangent there. We also will have a horizontal tangent right here at that x-intercept. Believe it or not, there's one there. So when we go find the second derivative, it'll show up right there. All right, so for the second derivative, I went ahead and I found the derivative. 4x to the third minus 36x squared plus 96x minus 64, factored out of 4. And because you have so many 4s at the beginning of the function, you could probably divide out a 4. And I did that through synthetic division, and you know how to do that stuff. So I went ahead and factored it for us, and yep, 2 4s still exist. And an x minus 1 was created. So there's going to be my 3 critical numbers at 1, 4, which appeared twice. All right. So I told you that's where that one horizontal asymptote was going through the x-intercept at 4. So again, looking at where do we increase and decrease, if we do this all by hand, remember, look at that leading term for your right-hand behavior as a positive, but because this occurred twice, it doesn't alternate and stays positive. Happened once, it alternates. So we are increasing from 1 to infinity the whole way. This is not a vertical asymptote. Remember, that was an x-intercept, so there's no break there. We're decreasing from negative infinity to 1. Looking at our pattern here, I am decreasing to increasing. So at 1, that's going to be a relative min. And to have a relative max, I have to be increasing and change to decreasing. Well, I don't have that, so that's a none. So to find this y-coordinate, I need to go to my graphs now and punch these in to find those values. So if we look at the graph, Here again, blue is the original function. Here's the red and the black. Again, two ways to do the derivative. Either type it in or have the calculator generate it for you. And finding that x-intercept right there for the derivative would give you that critical number 1. And yes, this is an x-intercept right here on the black curve. We already know that's a 4, so that would be another 0 that you'd have to find for your x-intercept. All right. And again, remember, if you're working with the black curve, you might get rounded values. Just to show you, this is 0. That's negative 0.5 zeros and an 8. That's close enough to 0. All right, so we found the relative min. I went back to my y1 equation on the top, hit the trace button, typed in the 1, and I got negative 27 for the y coordinate, so there's my min value. That's pretty quick and painless with the calculator. Oops. All right, and going back just again to verify, yes, there was that 0 on my derivative curve at 4, 0. And again, it happened twice, and it makes that parabolic curve right there in black. So probably when we take the derivative of that again for the second derivative, it's still going to be hanging out there because there is a horizontal tangent at the bottom of that parabolic curve right there. So it's going to show up again. All right, so second derivative, I went ahead and found that. 12x squared minus 72x plus 96, set it equal to 0, factored out the 12. I have a trinomial which I can factor to x minus 2x minus 4. Sure enough, the 4 showed up again. So my points of inflection are going to be 2, comma something, and 4. And we already know we're at 4, 0 because we've already found that once before off of the original graph, so we know that's a point of inflection. So make your number line, plot your 2, plot your 4. Right hand behavior, I got a positive 12x squared, so this starts positive, and then we alternate because these numbers only occurred once. So where do I concave up? Negative infinity to 2, 4 to infinity. Concave down between the 2 and the 4. So to find our y coordinate here, I did a variety of possibilities. Notice I don't have y1 listed here. It didn't fit on my window. But here are 3 different ways to find the second derivative. You could use the derivative functions that you have. Okay, you could take the derivative of y2. That's the one we typed in that we found. That's the second derivative. That's the first derivative here, y2. That would now make the second derivative. Or y5, you could take the second derivative of the calculator's first derivative graph. That too will work. And 6 down here, I just typed in when we found it. Okay? So 3 different colors will represent the same graph. So when I plotted it, sure enough, there's the blue. That's my original. There's in black, first derivative. Okay, here we go. There it is in pink, being covered up by green, and then it's going to be completely covered up in orange. All right. While we're here on that second derivative, here's an x-intercept at 2, 0. That verifies that point of inflection value for x. And of course, we have the one over here at 4 as my second point of inflection, and we already knew it was at 4, 0. And like we said, we had to go find the value on the original function for 2 to find out what's the y coordinate for your point of inflection. So that's going to be a negative 16 for that point. And so while we're here, you can begin to see, looking at the orange graph, here's my positive y's. That's my positive region up here. And sure enough, from this point, you can see that it's concaving up. All right, then from 2 to the 4 over to here, this is where my orange curve is negative y's. That's where my original graph has to concave down. Then at that 4, now my orange has all positive y's, and now notice the blue graph is concaving up. All right. Okay, next example, we're going to work within this window here. Now we have a fraction. I'm really starting to like this calculator stuff, so I'm going to kind of just stick to mostly calculator, and I'll throw in the work without showing the work. Give you the right answers from there after I worked it out. But what we can see that from x squared on the bottom, we're going to have a vertical asymptote at x equals 0, and it's going to occur twice. The horizontal asymptote, you have leading powers that are the same, so the leading coefficient ratio 1/1 is your horizontal asymptote. My y-intercept doesn't exist because it's going to be 3/0. I look at that constant ratio, so there's no y-intercept, which also makes sense because we had a vertical asymptote at x equals 0. That's my y-axis. And my x-intercept, well, that's too difficult to factor and solve, so let's just go right to the calculator and find it. So I typed in the original function, and now I went more calculator here. I'm asking for the derivative of y1. That will be the first derivative, and then this will be the second derivative because I'm taking the derivative of the first derivative. But I left the equations off so they won't clutter the screen. So here's my graph, and I hit trace right away, which puts you at the center of the screen. And you can see there's no y value, so that verifies my vertical asymptote. And you can see on both sides of 0, they're going up to infinity because there's no sign change there because it occurred twice. So we want to find this x-intercept here and the one over here. So we'll do the 0 command. And the other thing I wanted to point out too is that here is your horizontal asymptote at y equals 1, which is going to be important to understand because this part of the curve is not going to go down and cross the x-axis anywhere over here to the right, so you don't have to worry about more x-intercepts. That horizontal asymptote is verifying that there's nothing past here. And the same thing over here. It looks like it's going to go up and then it might come back down. No, it has to approach that line, so it's never going to come back down and cross the x-axis. So we only have these two values. So my first 0 over here to the right is negative 0.5458619. And my second one is at negative 6.5413881. And look, it gave me an ugly, ugly y value. But remember, e to the negative number, that's 0. There is 13 zeros in front of that 2. That is really rounding to some small decimal places. So that's a 0. All right. So just out of giggles, I actually took the numerator, solved it by the quadratic formula, or you can complete the square, and I came up with these values. And because of this number here, I went to my calculator and I typed in the negative 7/2 minus the square root of 37/2. I knew that one was to the left because adding is to the right. I hit enter, and sure enough, it is a 0, and there's my same negative 6.5413881. So it's there. I just cannot believe it rounded out to 17 decimal places. That was ridiculous. All right, now for our y sub 2, our first derivative test. So let's go to the equal sign, turn it on, get the graph, and this is everything in red. And so right away, to find your critical numbers, we have to find where it crosses the x-axis. So I went ahead and did the 0 command. Negative 0.857144, and also don't forget, all right, you're going to have a vertical asymptote along with your horizontal asymptotes. Thank you, thank you, thank you. All right, so here we can see that horizontal asymptote with that vertical asymptote right there. So we have one critical number, that's the decimal, and I did go do the work, solved it, found the derivative, solved it. It's actually negative 6/7, and our other critical number is 0. All right, but now it's occurring 3 times. So if you recall in class, we noticed that every time you took the derivative using the quotient rule, that denominator kept increasing by 1 on the power. So it was x squared originally, then it's going to be x cubed after we do the simplifying. So it occurs 3 times. So here I put a dashed line to remind myself it's a vertical asymptote. This is a tick mark. And again, now looking at the red curve, we are positive y's only from -6/7 to the vertical asymptote of 0. That's the only place we're positive. Every place else in red is below the x-axis. Those are negative y's. So that's where we will be decreasing. And if you look at the blue curve, everything here to the right is going downhill. So my tangents are all negative. And over here on the left, the only place I'm increasing is after this horizontal tangent right there, where that's going to be my local min. Then that's the only place I'm increasing. Otherwise, I am decreasing all the way to here. So we'll increase from -6/7 to 0. We're decreasing everywhere else. -infinity to -6/7, 0 to infinity. My min value, we said, was already at -6/7. I have to plug that into the blue curve to go find that value. There was no maxes here because you can't go from increasing to decreasing and say you have a max over the vertical asymptote. So we only have the min. So going to our y1 to plug it in, so I typed in -6 divided by 7 for x, and it returned a fractional answer for me, because in my mode window, my answers are in automatic, so there's the y coordinate. Now, a quick note here, that if WebAssign gives you an interval to work with, all right, I took some liberties here. I gave the intervals because that's the screen size that makes the picture look the best. But if they want it as an interval, you don't go to -infinity, infinity. You just stop at your x min and x max. If there's no interval given, then we go to -infinity and to infinity. So please keep that in mind when you fill in your answers. All right, so like I said, there is my minimum, my local min value right there. Second derivative. Okay, now we highlight y sub 3 to take the derivative of the first derivative. I look at my graph, and again, once that black curve came up, I wanted to find that x-intercept because that's going to be my point of inflection x value, -1.285716. And again, we also have the vertical asymptote at 0. And that 0 is occurring now 4 times. Remember, we said every time you take the derivative using the quotient rule, you increase that power on the bottom. And I solved the second derivative. The top numerator is actually -9/7 for that point. So that point of inflection, I went back to the first curve, y1. I typed in -9/7, and it returned -71/27 for me. So that's the actual point of inflection. So again, 0 is a vertical asymptote, which occurs actually 4 times. This POI only occurred once. So again, we look at our black curve. Okay, here this black curve has all positive y coordinates. So that region's going to be positive, and it's positive from that -9/7 to 0. And the only place our black curve is below the x-axis is to the left of -9/7. So this is where we can tell where we concave up and concave down. We are concaving up on these 2 intervals here. Now, because of that vertical asymptote, it doesn't concave up the whole entire time. As you can see with the blue curve, we're concaving up here, and then on the other side of the vertical asymptote, that's considered concaving up. From this point to the left, everything is concaving down on the blue. So that's -infinity to the -9/7. So this is how we can use our calculator just to improve these values. Now again, I found the exact values. If the WebAssign uses decimal, I'll be accepting both on the test if we're asking to do everything by the calculator. All right, that's it for this section. Thank you.